Hello everyone, it's Benny, and welcome back to the 3D software rendering tutorial series. Last time we got texture mapping working, but it had a bit of a distortion, a little bit of a warp to it. And today we're going to be addressing that. First off, we're going to talk a little bit about some other issues with the texture mapper, and we're going to address those. Then we're going to walk through some of the theory as to why that warping is happening and how to address it. And then finally, we're going to fix it by implementing true perspective-correct texture mapping. So with that, let's go ahead and let's get started. So, since last time, there's actually been a few things I did off-screen. First off, for source Y, this should be texture.getHeight, not getWidth. I actually did change this during the coding of the last video. You could even see that on GitHub. But unfortunately, I didn't get a clip of that in the final cut, so sorry about that. Now, something I didn't do in the last video is with these X and Y steps. We actually shouldn't be stepping text chord X and text chord Y by the gradients steps. We should actually be recalculating them here. And you might be wondering, well, Benny, why on earth would you want to do that? Shouldn't those give us the exact same values? And they should, mathematically. The problem is with floating point precision. If you get edges that are really, really close together, you can actually get some floating point error in the gradient calculation creeping in and causing the X pre-step to step these outside or past the right edge. And well, you don't want that because that'll give you a ray out of bounds issue, and yeah, it's just not a pleasant situation. So what you actually want to do is recalculate it here so there isn't that sort of floating point error from the gradient calculation. Now, I'll admit, the way floating point error accumulates and propagates through various calculations is an area that I need some improvement on as a programmer, or at least I'd like some improvement on. So, if there's some other issue in here that I'm not aware of, or there's some way to do this better, let me know, because again, floating point precision error propagation, it's something I could use improvement on, I think. So anyways, that means we actually don't need gradients in draw scanline, or scan edges, we can just recalculate it here. So there you go. And that's all I did off screen. So, now let's talk about that weird warping effect we see in our texture mapping. What is that? Where does it come from? And to do that, we're going to reevaluate some of the mathematics we're doing for our texture mapping. So, we have a triangle, and at the triangle we have all these vertices. All these vertices have some X and Y position, and some C. That represents anything we can interpolate across the face of the triangle, whether it be lighting, color, or in this case, texture coordinates. And the idea is, with the C value, based on the gradient stuff we talked about in video 13, I believe, we can interpolate linearly any value across the triangle. So anything we can represent in a linear equation, like this, we can interpolate accurately across the triangle. But this sounds all well and good, but there's a small issue we aren't quite considering yet. And that is perspective. These aren't just vertices of some arbitrary triangle, these are vertices in a perspective-correct triangle. So let's look at our perspective equations again. Now in video 5, I believe, we came up with this equation for generating proper perspective. And for simplicity, we can ignore the tan f of v over 2. That's just some constant. We can just simplify that to some value over z. That gives you the projection. So what we actually have for our vertices, for our final vertices, are these x and y aren't just being directly used to draw the triangle. We're taking those x and y values divided by z to draw the triangle. And the first thing you might notice is, whoa, wait a minute. We aren't doing any of that perspective adjustment for our interpolant. Is this going to cause an issue? Well, maybe this will only cause an issue if dividing by z will somehow cause interpolating this value to not be, well, a real linear equation. So, just to clarify, our whole problem here, our whole question is whether or not dividing by z somehow stops our interpolation from being linear. Because we know from the gradients video that if we just use x and y, if we just use this with no perspective correction, then yeah, all the math we did in the gradients video, all the math we're doing right now, is valid. But does our perspective projection, does dividing by z have some effect on that? And to figure this out, we're going to do a little bit of a devilish trick here. Now we know from our perspective projection that x divided by z gets us our final projected x value. With a little bit of algebraic manipulation, we know that means if we multiply our projected x value by z, that should give us our original x value. And we know the z value at every single vertex. So, if our interpolation really is linear, and dividing by z really doesn't affect it, we should be able to take this z value at every vertex, interpolate it across the triangle, and then every pixel we should be able to multiply z by our projected x value, and get our original x value. Seems reasonable enough. So, let's see how well that works out. So our ultimate test here is, can we calculate x from z in some linear fashion? The exact values of a and b here don't really matter. The only question is it a linear equation? And well, so let's solve this. We know x equals x projected times z. So what we're really trying to do here is solve for z. So what I can do is I can add a times z to both sides and factor out the z. So, subtract az from both sides and factor out the z. Sorry about that. And then, all I have to do is divide by xp minus a, and there you go. I've got my equation for z. Now, I don't know about you, but that most certainly does not look like a linear equation to me. So, yeah, no, this is not linear. And this is the reason we're experiencing that weird perspective distortion. In fact, even if you look at just our interpolated color pyramid, you can actually see that looks a little bit off too. And it's because our interpolation scheme is accurate for linear interpolation. But because we have perspective correction, we're going to have to adjust our interpolation for that. We're going to have to do perspective correct interpolation across the triangle for things to really look valid. So how do we do this? We know the z value isn't linear, so what do? There's a little bit of an interesting trick you can do here, actually. What happens if I just take the reciprocal of this equation? Well, I get something like this. 1 over z equals 1 over b times xp minus a over b. Seems simple enough, but I don't know about you, but this looks an awful lot like a linear equation. So yeah, interestingly enough, 1 divided by z is linear across the face of the triangle. And if you think about it, this does make some sense, since we are dividing by x in and y in over z, so that's multiplying by 1 over z effectively. So if you think about it, yeah, it does make some sense. But, you know, that's really some interesting math in my opinion. So we're going to take advantage of this. We're going to interpolate 1 over z across the triangle, and we're going to use that to correct our values. We're going to use that to get perspective correct values at every pixel. And that is the secret to perspective correct texture mapping, and the secret to just perspective correct interpolation in general. So, I went ahead and did a lot of the stuff in Edge and Gradient off-screen, because that's the same thing we do for every new interpolant. We add the value and its step to the Edge class, we add a getter for the value, we do the same initialization process in the Edge class, we get the appropriate gradient value for min-y index, we get the appropriate steps and multiply them by the pre-steps, we calculate the step from the gradient steps, and also don't forget to actually step the value in the step function. And there you go, that's all we do in Edge. In Gradients, it's also mostly the same, but there is some new stuff I'm going to talk about in a moment. We we're going to still need a new float array and new values for the steps. We're still going to need a getter for the float array and the steps. And ignore those functions for the moment. We're still going to need to initialize the float array. We're going to need to initialize them to values from the vertex, which I'm going to do on screen because it's a bit different. And we're still going to need to calculate the x and y steps. And now you might notice I've refactored this into a function. It's doing the same thing as before, I just decided to refactor it into a function because I figure we're reusing that stuff enough now. It warrants its own function. So there you go. So now for actually coding this. This is 1 over z. So we're going to do 1 over, for instance, for value 0, for index 0, min y vert, get position. I also added for getter for that in vertex. It's pretty simple, just gets the position. There it is. And yeah, so anyways, we're going to do 1 divided by the position. And you might think, oh, we're going to divide by the position.getZ. No, we're not going to divide by the z value. We're going to divide by the w value. As I mentioned a bit earlier, I'm going to talk more about later. Each vertex has 2 z values. One is the value we use for perspective, and the other is the z value we use for occlusion. The w component is the one we use for perspective. So yeah, just be careful of that. And another thing to mention here is that I've actually done a bit of cheating in the vertex earlier, where we're not dividing the w value when we do perspective divide. We're actually keeping it around for this very reason, so that we have it here. Just a nice, convenient way to do that, other than, oh, let's create a whole new variable to store it, preserve it through all the swapping and all the other operations, pass it through 10 million functions. No, I say just keep it around. Why? Why not? So yeah. Anyways, I'm going to go to gradients now. Anyway, so yeah. So we're going to do 1 over the w value. And we're going to do that same sort of thing, except with mid y vert and max y vert here. Now, to make things perspective correct, we're actually going to have to change how we're interpolating text coord x and text coord y. We're actually going to want to multiply all these values by 1 over z of the appropriate index. So effectively, we're doing a perspective divide on all the extra coordinates values. We're dividing by the perspective z. And that might seem just a little bit weird. Like, why would we want to do a perspective divide here? What's the point of that? As we talked about earlier, not everything can just be linearly interpolated across the face of the triangle. Sometimes the fact that we're using perspective here, we're dividing by z, that can throw that off a bit. And textual coordinates are one of those instances. Otherwise, we wouldn't have that ridiculous warping effect in the first place, and we wouldn't be sitting here doing all this ridiculous math to avoid that. But if we can't interpolate the textual coordinates directly, what we can do is we can move them through the same transformation as the x and y. In this case, that's divided by z. And no, that really doesn't help us that much. We don't really care what the textual coordinate divided by z is at a pixel. But if we know what 1 over z is, well, we can find out what actual z is. And if we know what z is, and we know what the textual coordinate divided by z is, we can multiply the textual coordinates that are divided by z times z to get what the textual coordinates actually should be. And that's the whole chain of reasoning here. We're dividing by z, so it's going through the same transformation. We can't linearly interpolate just this, so we're dividing by z. And then later on, we're going to multiply these values so that we can get the actual value. And that's the sort of workaround we're doing. I know it's a little bit tricksy, but hopefully that makes some sense to you. So now, let's go in render context. We've done really most of the hard work, unless I've screwed something up. So let's just make sure I haven't screwed anything up. Okay, should build. Don't run or it will crash. So anyways, now we're going to need a new float here for 1 over z step. And I guess we can call it x step, but it doesn't matter. Alright, I'll call it x step for consistency. And this is just going to be right.get 1 over z minus left.get 1 over z. Same calculation as before, over xdist. So we're recalculating here so that we have nice precise values. And our 1 over z value initially going to be, well, similar. We're going to take get, not that, 1 over z, there we go. And we're going to add 1 over z step times x pre-step. So this is our initial 1 over z value. Now at every pixel, our float z, that's going to be 1.0 divided by 1 over z. So that gets us our actual z value. Now our text coord x and y here, remember, these are now multiplied by z. They're divided by z. So we have to multiply by z to get the actual, well, to get the actual value of the texture coordinates x and y. And if we build, that should build. If we run, something's clearly gone horribly wrong. So, one moment. Okay, I'd actually gotten in here, I'd gotten this and this swapped around, so yeah, be careful about that. And inside render context, I'd completely forgotten to actually do the 1 over z plus equals, well, 1 over z x step. So make sure you do that. And if you do that and build and run, you get a texture mapped triangle rotating with perspective correct texture mapping. And it looks great. The only thing you might notice is that there one band of pixels on the x and one on the y-axis that seem to be vibrating a bit. And that's because they happen to land exactly at 0, 0. So yeah, that's a bit odd. But if I go to, oh, where is it? Main. If I do a different rotation, one that doesn't keep those perfectly aligned with everything, like, oh, let's just rotate around every axis at once in Euler angles. So if I do that, build and run. There you go. Now you get to see the triangle completely flat and looks nice. So there you go. Now you really do get to experience perspective correct texture mapping in its full glory. So, that's great, but, you know, playing around with just one triangle's getting a little old, getting a little dull, getting a little bit boring. How can we take our new texture mapped triangles and start really building a 3D world out of this? Find out next time on the 3D software rendering tutorial series. I hope you enjoyed, I hope you learned, and I'll see you in the next video.